I was going to put all 4 examples in the first examples video, but I kind of got a little bit rambly in that first example, so I'll put the second 2 examples into this video. So here is another example from the book. This is problem 1, and we're going to work on part C. Part A and B are part of your homework for this section. In this problem, we're wanting to find a basis for the row space, the column space, and for the null space of this matrix here, which we could go ahead and call this matrix A. So that we'll just say A is this matrix here. Again, we've already seen that finding a basis for the row space and column space just involves putting this into row echelon form. And it turns out doing the same, putting it into row echelon form will help us find the basis for the null space as well. So again, we're just going to do Gaussian elimination. Everything always comes down to Gaussian elimination, it seems. So we're going to keep this first row. We're going to try to change that 2 and 3 to zeros. And I'll go through this a little faster than I have with some of the other ones. So what happens here? Well, we'll end up with a -5, a 7, and a 0 here. A -5, 11, and 3 here. We do need to actually have leading ones, so we will have to go ahead and divide one of these rows by -5 to change the first entry, the first non-zero entry to a 1. So we are going to end up with fractions in this problem. That's just a little bit unfortunate, but it's normally what happens. We don't always get lucky about all that kind of stuff. So we'll still have zeros here. We're going to go ahead and just divide this row by -5, so we have a 1 here and a -7/5 here. But we still have a 0 there. That's nice. And then we need to cancel out the other -5 to get a 0. And actually, it's a little easier to think about what happens if we just look at the original rows. Just kind of subtract the second row from the third row. That will get rid of that -5 immediately, and it will go ahead and leave us with an 11 here. And, sorry, not 11. Need to look at the right spot in my notes. Obviously, it was 11 to begin with, but the 11 becomes a 4, and because there's a 0 here, that doesn't change that 3 from being a 3. Finally, we're going to have to change that 4 to a 1. So we'll go ahead and divide the last row by 4. Let me get the rest of this stuff in here. The fractions are actually going to take up the most space, so I don't want to run out of space. There we go. So from this matrix, we can actually already get a basis for the row space and a basis for the column space. Remember, our basis for the row space, we can just look at all the rows that have survived, all the rows that are not all zeros, which in fact is all the rows this time. So for the row space, we can go ahead and take, well, either all 3 of the rows of our row echelon form matrix, or because all the rows came from rows in A, we could use the same rows as in A. So it just really depends on what you want. We could make a basis where it's 1, 3, -2, 1, and then 0, 1, -7/5, 0, and then 0, 0, 1, 3/4. Or we could go back and use the rows from A, or we could even, if we don't like having fractions in it, we could go ahead and just multiply the rows by whatever common denominator to get rid of those fractions. So we could use, for an example, 1, 3, -2, 1. That one's common to all of these. But then, so we don't have the 5 on the bottom, we could go ahead and make this 0, 5, -7, 0. And then 0, 0, and then 4, 3. That would be a basis for the row space. It's one possible basis. For the column space instead, we're going to look at what are our leading ones. So we have a leading one here, we have a leading one here, and we have a leading one here. We're going to take the same columns, or the same column positions in matrix A. So we have leading ones in columns 1, 2, and 3. So we're going to take columns 1, 2, and 3 from the original matrix A. So here, the first column of A is 1, 2, 3. The second column is 3, 1, 4. And the third column is negative 2, 3, 5. And that is the basis that we get from this process. If we wanted a different basis, like we have a lot of possibilities for the basis for the row space, the column space doesn't really give us as many options unless we're willing to do something else. In this particular case, we did kind of get lucky. Notice that these are three-dimensional vectors. These are vectors in R3, and we did get 3 of them. Therefore, this must actually be a basis for all of R3 in the first place. So any basis for R3 would be a basis for the column space because the column space of this matrix is in fact all of R3 to begin with. But that's not something that happens in general. That's just kind of a specific thing to this particular matrix. Now, what about the null space? How are we going to do that one? Well, what is the null space? Remember, the null space is just all the vectors that if we take A times a vector, we get 0. So let's actually go ahead and do this on a separate page so we have a little bit more space for it. I'm going to go ahead and write out the matrix A. And then we are going to multiply this by a column vector, x. And keep in mind this has to be a 4 by 1 vector, because it has to match the size from the matrix A. And the result of this will actually be a 3 by 1 vector of all zeros. We want it to be all zeros for the null space. So this is A times x equals 0. Of course, doing Gaussian elimination doesn't change. Well, it won't change the solution set for this linear system. And because we have all zeros here, it won't change this vector either. So all the Gaussian elimination that we did is still valid here. So we're just going to now write down the matrix U. So we have 1, 3, negative 2, 1. Then we had all our zeros here. We had 1s along here. But then we had our negative 7/5, 0, and 3/4. That matrix is our matrix U, still times the same x's. That x looked like a 3, sorry. This is supposed to be a 2. Then we have x3 and x4. And that's still going to give us the same zeros over here. In other words, we can express these x's in terms of other x's. Basically, we have equations here. So our last equation is x3 plus 3/4 x4 is equal to 0. Or in other words, if we pick something for if we pick something for x4, that will determine x3. If we pick x4 equals 1, then x3 is going to have to be negative 3/4 times x4 is 1. So actually, let's instead of picking 1 for x4, let's go ahead and pick something that will actually not give us any fractions. Since I already know what's going to happen here, and instead of just picking 4, I'm going to go ahead and pick x4 is equal to 20. Because we do have this 5 on the bottom here, so we are going to want to have to somehow cancel out that 5 somehow. Basically, we're using a common denominator. And if x4 is 20, we plug 20 into here, we get x3 plus 15 is equal to 0. So x3 is going to be negative 15. x2, well, now we have to use another equation from our row echelon form. We actually have the x2 minus 7/5 times x3 is equal to 0. If we go ahead and use our answer for x3, plug it in here, we get x2 plus 21 is equal to 0. So x2 is going to then have to be negative 21. And then finally, we can do exactly the same thing, doing all this back substitution to find out what x1 will have to be. And we get that x1 is going to be 13. Now, this did depend on a choice of x4. If we picked a different x4, we would get a different vector. But everything is just going to be a multiple of what we pick for x4. So it turns out a basis for the null space is just what we got here. Of course, we need to flip it upside down. X1 is the one on top. So we'll have 13, negative 21, negative 15, 20. Or if we prefer, we could divide everything by 20 and have fractions. But the point is that every vector that gives us 0, 0, 0 when we do this multiplication is going to be a multiple of this vector. This is a basis for our null space. Our final example is actually going to be related to what you're going to be doing in problem 2, but I don't like the problem that I didn't assign to you, so I'm made up a different problem. This is actually going to be a bigger R. It's going to be an R5 instead of what you had to do in problem 2, but it'll at least demonstrate the process of what you're going to be doing there. So we're going to take 4 vectors in R5. These actually will span a subspace because every collection of vectors spans a subspace of whatever vector space they're in. But we don't know what the dimension of that subspace really is. We have 4 vectors, and so it looks like the span would actually be 4-dimensional, but we do not know that. We don't know if these are linear independent vectors. And it's actually a tricky question to determine whether or not these are linear independent, or how many vectors we would have to get rid of in order to make it linear independent. That's the kind of stuff that we'll be determining right now how to actually solve. So we're going to take these things, and we're going to figure out what is the dimension of the subspace. What we can actually do is think about these as columns of a matrix. So we're going to form a matrix where these are the columns. So now we have a 5x4 matrix. And the column space of this matrix is, in fact, the space spanned by the original four vectors. So everything that we've been doing to determine a basis for a column space is going to apply to our original problem. So how do we find a basis for the column space? Well, all we need to do is do row echelon form. Use Gaussian elimination. So that's what we're going to do. We're going to take this matrix. We're going to try to change this first column to a 1 with all zeros. We're going to leave the rest of the stuff alone in that column, in that row. We're going to get some fun numbers in here. So our first row, actually, our second row, the first row that's actually changed, will be 0, -9, -46, -19. Our next row is going to be 0, -1, -7, -3. Then we have -4, -10, and 6. And then finally down here we have -10, -15, and 25. So quite a few calculations there that I skipped over, but hopefully the process of doing that is fairly well known to you guys by now. I mean, we have been doing a lot of Gaussian elimination. I hope by this point we know how to do that. Then what do we do? Well, now we want to pick a pivot. So before I went and picked this 1. The 1 was in a nice position and was very easy to use. Picking another pivot, well, actually, let's go ahead and pick this -1. I'm going to multiply that row by -1, and I'm going to move it to my second row. So my first row is going to stay 1, 2, 3, 4. My second row is now going to be 0, 1, 7, 3. So not too bad there. We're still going to have zeros for the rest of the first column. And in fact, we are going to use this new pivot to change everything below that 1 to a 0 in the second row. Now what does that do to the rest of it? Well, our third row is now going to be 8, 8. Our fourth row is going to be an 18, 18. And our fifth row is going to be a 55, 55. So hopefully you can kind of see where that's going. Because we have one last step for our Gaussian elimination. That first row is going to stay the same, and second row is going to stay the same. Our third row, we are going to have to multiply by something to change that into a leading 1. Well, let's just divide everything by 8. So we just have 0, 0, 1, 1. Obviously, we still have zeros here. And if we then use this 1, 1 to cancel out these two, this 18 and 55, hopefully it's not too hard to see that they'll also cancel out the other 18 and 55. So this is going to be our REF matrix. If we wanted to find a reduced row echelon form, obviously we'd go ahead and change this 2 and this 3 and the 7 all to zeros and see what happens to the 4 and 3 that are at the ends of those first two rows. But we really don't need to do that to solve the problem. So we'll go ahead and just stop at the REF. Now note, we do have exactly 3 leading 1s. So what are our leading 1s in this problem? We have a 1 here, a 1 here, and a 1 here. What does that tell us? That tells us that the dimension, instead of being the 4 that we originally might have thought of, is actually going to be 3. We actually do not need all 4 of these vectors for the span. In fact, just the ones that correspond to leading 1s, the ones, oops, let me circle all of the vectors. Only the ones that correspond to columns 1, 2, and 3 need be there. We only need these first three vectors to span the entire span of those original 4 vectors. And in fact, that is going to be a basis for that subspace. All right, that's all four of our examples. I will refer back to some of these in our theorems video. We'll go through some of the results, some more some higher tier results, you might say, some more important relationships that we might have already have seen from our examples, kind of formalize those into actual theorems. So I'll see you guys in those in that video.